All right, in this tutorial on colligative properties, first we were going to define colligative properties and kind of say what those properties are, and then we're going to talk about those individual properties and how the concentration of a solution would affect them. All right, so what is a colligative property? So a colligative property is a physical property of a solution that depends on the ratio of the number of solute particles to the number of solvent particles in the solution, not on the type of particles. So what I mean by this is that a colligative property is a property of a solution that can be altered or changed by changing the concentration of that solution. There are quite a few colligative properties that we can talk about, but we're going to limit our discussion to the following three. So there's vapor pressure, freezing point, and boiling point. So all solutions have these three physical properties that are measurable. And by adding or removing solute or making different concentrations of solutions, you can actually change these three properties. So let's talk about how the concentration of a solution or how the amount of solute per solvent would actually affect each of these three colligative properties. So we're going to go ahead and start our conversation with vapor pressure. All right, so let's define what vapor pressure is first. So what we have here is a container with pure solvent like water. And these solvent molecules are randomly moving throughout the solution, and of course the ones nearer the surface are going to, at some point, escape the solution and turn into a gas. So this is called evaporation. And so that means that these molecules of water that have gone from the liquid phase into the gaseous phase are kind of hovering above the solution. And they will, of course, create some pressure above the surface of the solution. So they will actually push down onto the surface of the solution. That is called vapor pressure. And you can imagine that the more of these molecules that evaporate, the more they'll push back down onto the surface of the solution, and the higher the vapor pressure will be. So let's say you've added a solute, like to your solvent. So for example, we had our water molecules, and then we added to that some sugar. So what you're going to find that happens is these sugar molecules, or these solute molecules, because they get in the way, and also because they are interacting and holding on to or attracted to your solvent molecules, they are going to sort of block the pathway. The solvent is too busy interacting with the solute to evaporate. So that means less molecules are going to escape into the gas phase, which means that less molecules will be hovering above the surface of this solution, and so then of course you just have less molecules pushing down. So what that's going to do is it's going to lower the vapor pressure, and it does that because you have a solute that is holding back your solvent molecules from evaporating. So the short and skinny is that when you add a solute to a solvent, that is going to lower the vapor pressure of your solution. All right, so we needed to discuss, the type of solute that you're dissolving in your solvent. So, you can have solutes that are ionic, and you can have solutes that are covalent. And they do different things when they dissolve. So something like sodium chloride, which is an ionic solute, when you dissolve it into a solvent, it splits into two ions, a sodium ion and a chloride ion. So what that tells me, or what that means, is that if I have 1 mole of sodium chloride, I'm going to end up getting 1 mole of sodium ions plus 1 mole of chloride ions. So I'm going to get a total of 2 moles of pieces. Whereas a covalent solute, like glucose, C6H12O6, when I take that solid and I dissolve it in a solute, it stays one molecule. So if I have 1 mole of glucose, what I'm going to end up with is just 1 mole of pieces, or 1 mole of particles. So your ionic compounds actually break into more than one piece, and then you end up with more solute pieces floating around in your solution than your covalent solutes would. And what that really means is that ionic solutes would have more effect on a colligative property like vapor pressure than covalent solutes would, or at least the same amount of ionic solute would have more of an effect than the same amount of covalent, because ionics break into pieces. Freezing point is the next colligative property that we're going to talk about that would be affected by the concentration of a solution. So what is a freezing point? The freezing point of a solution or of a solvent is the temperature at which it turns from a liquid into a solid. So for example, water has a freezing point of 0 degrees Celsius. So its freezing point is 0 degrees Celsius. So what happens when something freezes? So this right here is a group of water molecules, and they're liquid water. And when they freeze, what happens is they lose a bunch of energy, and then the molecules slow down, and they start to form these little crystal patterns. So you can see that these are forming these little hexagon-shaped patterns. And they do this naturally when they freeze at a particular temperature, and that's for water, again, 0 degrees Celsius is when this starts to happen. When you add a solute to your solvent, in this case water, what you'll find is that the solute particles actually interrupt the water molecule's ability to form these little crystal patterns. They actually get in the way so that they can't form these little crystal patterns. So what that does is it means that the water or the solvent, which is water in this case, to be able to form those crystal patterns, it has to be at a much lower temperature. So the short and skinny is that when you add a solute to your solvent, that is going to cause the solvent to freeze at a lower temperature. So it's lowering the freezing point. So, for example, salt water. Salt water is going to freeze at lower than 0 degrees Celsius, where pure water would freeze at 0 degrees Celsius. So we're lowering the freezing point. This is really useful in the winter. I mean, this is why we salt the roads. We do this so that the water on the roads would freeze at a lower temperature. So it has to be much colder for the roads to freeze over so we don't go sliding around. Also, it's the reason why we add antifreeze to our cars. We add antifreeze to our cars so that we can get down to a negative 64 degrees Celsius outside before the solutions in our car start freezing. That's pretty dang cold. So, we can run, say, an Arctic cat, in the Arctic without having to worry about the solutions in the car freezing. So it's possible to calculate these changes in freezing point that you would have by adding a solute to a solvent. And you can imagine that the more solute you add, the more it's going to interrupt that freezing pattern, and so the lower the temperature would have to be to freeze that solvent. So you can actually calculate this, and that's called, by the way, calculating a freezing point depression. Depression just means lowering, right? So how much is the freezing point going to lower or be depressed when we add a certain amount of solute to a solvent? So to calculate freezing point changes of a solvent, you will need this fun equation right here. So this equation, delta TF equals IKFM. The parts of this equation are as follows. Delta TF is equal to the change in freezing point of your solvent. I is called your Van't Hoff factor of your solute. And what a Van't Hoff factor is remember when we just talked about how ionic solutes will break down into more than one piece and covalent ones won't? Well, the Van't Hoff factor for an ionic solute is just the number of ions in the compound. So for example, something like sodium chloride has a Van't Hoff factor equal to 2 because there's a sodium ion and a chloride ion. And the Van't Hoff factor for a covalent compound, so a covalent solid's Van't Hoff factor, since they stay one piece, all covalent compounds have a Van't Hoff factor of 1. Kf is called your freezing point constant, and it's for your solvent. And to know your freezing point constant, you just have to look it up on a table of solvents. And you can see right here, we have a bunch of freezing point constants for a bunch of different solvents. And then m, little m, is molality. Molality is equal to the moles of solute divided by your kilograms of solvent. So you could actually replace that m with this and make your equation look like this instead. So let's do an example. So by how much would the freezing point of 0.5 kilograms of water be lowered by adding 3 grams of calcium chloride? So let's figure out what we have and what we don't have. So reading the question, we don't know how much the freezing point is going to change. So that's our question mark, or our X, what we don't know. Our Van't Hoff factor, because calcium chloride is an ionic compound made of a calcium and 2 chlorides, that means we have 3 pieces it's going to break into. So our Van't Hoff factor is 3. Our freezing point constant, we have to come and find our solvent, and our solvent is water. So we find that on this list, and we follow it over to Kf, and we see that our freezing point constant is 1.86 degrees Celsius per molal. Moles of solute, we were given grams of solute, so I did a quick little conversion to get our moles of solute using the molar mass of our calcium chloride. And our kilograms of solvent is 0.500 kilograms. So I'm going to plug all of those numbers into this equation, and this is what I get. So 3 times 1.86 multiplied by 0.027 divided by 0.500. And if I'm not mistaken, you should get 0.30, and of course it's degrees Celsius because it is your change in freezing point. So the change in freezing temperature is in degrees Celsius. So what that tells me is that my freezing point of water is going to be lowered by adding this amount of calcium chloride to this amount of water by 0.30 degrees Celsius. All right, and last but not least, we'll talk about how boiling point would be changed or altered by the addition of a solute to a solvent. So boiling point is defined as the temperature at which a liquid turns into a gas. So water, for example, boils at 100 degrees Celsius. So here we've got our pure solvent, water, and or just a pure solvent, and when it boils, its molecules will escape into the gas phase. By adding solute particles, what you're doing is you're putting something in there that's holding on to or preventing your solvent from escaping into the gas phase. And so solute particles really just get in the way. They hold the solvent particles back from being able to escape into the gas phase. So by adding solute particles to your solvent, you are actually increasing the boiling point. You're making the boiling point higher. So as with freezing point depression, you can calculate changes in boiling point. We call that boiling point elevation because you're raising the boiling point. And you'll recognize these equations, I hope. They're exactly the same equations that you would use for freezing point depression. The difference is instead of a B or an F, we have these little B's here. Delta TB is the change in boiling point of your solvent instead of freezing point. Your I, again, is your Van Hoff factor. Kb, in this case, is going to be your boiling point constants for your solvent. And then M is molality, which, of course, can be replaced with moles of solute per kilograms of solvent. All right, so let's do a quick example using this equation to calculate the change in boiling point if you took 14.1 grams of C2H6O2 and added it to 0.4 grams of chloroform. All right, so let's look at what we've got here. So we were given that we're looking for the change in boiling point. Our Van Hoff factor, our solute right here is a covalent solute. So the Van Hoff factor is 1. Kb for chloroform, our solvent, find chloroform on the list and find its Kb value, and you'll see that it's 3.63 degrees Celsius per molal. Moles of solute, we were given 14.1 grams of C2H6O2, so we need to turn grams into moles, and we get 0.227 moles. And then our kilogram of solvent was 0.4 kilograms. So we're going to plug all that into our equation for delta TB. So when we do that, we get 1 for our Van Hoff factor, 3.63 for our Kb value, and then we multiply by 0.227 divided by 0.4 kilograms, and we end up with 2.06 degrees Celsius. So that means our chloroform is going to boil at 2.06 degrees Celsius higher than it would have otherwise. It normally boils at, 61.2 degrees Celsius, so now it's going to boil at 2.06 degrees higher than that.